Okay. Right. We have another day of doing the risc-v instruction interpreter. Second day of doing that, and the sixth stream for this project in general. Okay, let's actually get to doing it. So. So yesterday we actually got most of like this part done for like a couple of the instruction types. We got I'm pretty sure all the arithmetic instructions are done. So the R type and some of the I type instructions. So yeah, now I think we should move on to branches today. So we'll give branches a shot. And in our header file, we have the core and the struct made, so just as clarification. So we have our core ID, program counter, the amount of registers, and yeah. And every time we make an instruction, if we're trying to like access the register, the value inside the register, we read the register, and then we write to the register whenever we're actually implementing the instruction, and then we break out. Since we're not returning, we have to break out. So, all right. So case instruction. Now we're going to do BQ, right? Yeah, BQ is our first branch instruction. So it's a bit different with branches. Like, for example, earlier, most of these would just be like reading one register and then reading another register, or like doing operations on these two and then storing it in a destination register. Now it's a bit different. We're not actually storing anything in registers. Branching is basically like when it reads that instruction for branching, you're branching to a different part of the assembly code. So it's going to be a bit different than these instructions up here. So, okay, so let's look at the description. So we have if the value in register 1 is equal to the value of register 2, the program counter will be added by the offset. So it'll be added by the immediate value. If not, it just goes as normal. So it increases the program counter by 4, which is how you normally go in the assembly code. So you will just move on to the next instruction. So let's see if we can write that in here. So I'm gonna get rid of this. So store, okay. So let's see, so we're first gonna need an if statement, and we're gonna need to read the register for rs1, and it's equal to reading the register of rs2. So if that equates, we'll be having let's just set a variable, so call it, what was it in our thing? I think it was like unsigned int. Yeah, unsigned int program counter. Unsigned int our program counter variable will be equal to the program counter plus the inst.immediate value that we had. So it's going to be offsetted by a certain value because we're branching to however far we need to go. If not, it will just be just adding by 4 to move on to the next instruction. And we don't need to write anything into a register, so we don't need this thing anymore. So it'll just be like this. It pretty much just be like this, I'm pretty sure. And let's try the case for branch if not equal. Should be similar. But let's see. So if you have branch if not equal, in this case, if it's not equal to the value in register rs2, in the rs2, and it essentially does the same thing. So it's basically saying, like, this is pretty much saying, like, if it's not equal to, we're jumping to the label, to the place that we want to jump to, so the offset amount. So it's kind of like the if statement, but like the not. These are basically just like if statements, but in assembly code, pretty much. That's how they represent. So this should be the same here. I just want to do a quick check with the logic with Claude and ask if the logic is good or if I need to, if I missed anything here. If we didn't miss anything, we can continue on with the rest of the things. Design immediately destroyed blockends. Clicking a new local variable. Oh right, wait. So, right. I totally forgot. We already have. We can't do it like this. We need to do core, not that core. We need to do it like this. So we can access the one in the struct, and not this. I think, right? That's how you access values in the struct, right? Well, let's just check. Let's just check. Or do we just write PC for the program counter? Okay, we can just write PC, okay. Alright, that makes sense. So, it's only needed when you're outside of the struct, referring to a static member or disambiguating in specific inheritance scenarios. Okay. I kind of want to clarify something though. So, let me see. Where did we need this? So, in this case, right, we did that. I want to know why we needed it here but not there. I'm just gonna clarify it. Right. Inside a member function body, you have direct access to everything in the struct. You can just, okay. But when you're defining a member function outside of the struct, in a separate CP file. Okay. So when it's relating to functions, we actually need to specify. Okay, that makes sense, yeah. Because they just think it's just a random regular function. Got it, good. Okay, that makes sense to me now. So that's why we didn't need it here, but we need it everywhere else. Okay. should be right now. Yeah. So now we can actually move further. And write the remaining instructions. So the next one we're working on is branch if less than. And for the case of this one, so if the value in source register 1 is less than the value of source register 2, then we are jumping to the offset, the place where we specify to jump to in our label, which would be the immediate amount. So it's basically the same, but we're just doing branch of less than. And okay, so in this case, we're looking for signed values, so we're gonna need to do a static cast on each. This is going to be the signed version, so we need to do a static cast. Static cast to signed integer. And then we're going to need to cast it back after. 1 second. Which value? Let's take a look. So if we go to BLT, okay, so in this case, would it be just signed RS1 or both signed RS1 and RS2 values? I think both signed, right? So we're doing a signed value of both, I believe. Before we move, we're gonna do this. Same here, static cast. And this should be right. I'm just gonna write the logic for both of these. Right. So that's done there. So now we're going to be writing the case for branch of less than unsigned. The unsigned value, we do the same thing, just unsigned versions. So in that case, it should just be regular, right? We don't need to cast it. So it'd just be this, like this, and remove the cast. Branch of less than unsigned, it should be this. Let's just take a look. Yeah. So now we can write the final two, which are branch of greater than or equal, and then sub. Branch of greater than greater or equal sign. Sorry. So let's just copy this value here. Right, greater than or equal to. It will just be flipping. That's it. And for this case, it's just flipping that, the outside version. So it should be right now. Let's check all the cases. Oh, right. My bad. Greater than or equal to. My bad. I didn't read it properly. Just flew over my head. Yeah. Okay, so what is next on the agenda? So we have J-type. Actually, it's not that bad. J-type's not that bad. I don't know why I said that. J-type is just this. It's pretty similar. It's just we don't compute using register source 1 and register source 2. Yeah, I will try doing it my own first. Thank you, Claude. Okay, so if we're gonna implement gel case now, right? I'm just gonna grab one of these random cases to copy paste here. Okay, so now we're in the gel instruction, which is a J-type instruction. So we'll basically jump in link. So this is kind of like function calls. So in this case, right, the program counter will be moving up 4. Okay, so the program counter moves up 4. We don't need an if-else statement. So, okay, I think I kind of got it, but wait a minute. So let's give it a shot. So if we write to the register, well, we're not writing to. Yeah, we actually are writing to register. So in this case, our first argument would be $rd, and the program counter plus 4. But then we're adding it by the offset, so something like this, I believe. Yeah, that's right. Okay. JALR is, let's see how JALR is. JALR is jump in link register. So now we're actually doing the value of register source 1 here. For register source 1, so JALR, so we're writing to register for destination register equals 4. It's the same, but instead here, it's not the program counter that moves up by 1, it's $1 that actually is being read first to find the value plus the median, which I will check here. It should be right anyways, but oh wait, so want. Setting the least significant bit of the result to 0. So our bottommost bit's gonna be 0, so we have to mask it. But what exactly are we masking? Like the bit itself, right? So that'd be like a wait. That's not gonna be exclusive, or that's not gonna be and either, because that would force most of it. So like the only thing I can think of is the OR operation. But if that 0th bit is 1, it's gonna still be 1, but is that bit ever 1? But except every bit except bit 0 stays unchanged, and 1 preserves. We can go check it in hex. So okay, wait, so I need to try and visualize this. Wait, let me try and visualize this game, guys. We're coming like the parameters in here for a second. And holy shit, it's too wide here. It's too holy light mode, bro. Alright, let's change it here. Okay. Let's change this to let's change this to wide. Okay, wait, so I'll just use like a couple bits for an example. So if you have 0, 0, 1, 1, 0, 1, 1, like 1, right? And we do a mask of 1, 1, 1, 1, 1. But this is 0, which is what we did. But like, let's just pretend all the other bits are here. Oh yeah, you're right. So anything that was already 0 will stay 0, and these will stay 1. Say 0, stay 1. So we'll basically get the same thing, but changes this bottom bit to 0. So yeah, that works. That works. It was like going like over my head for some reason. I don't know why. That makes sense. Setting a mask with 1 preserves except the one that you want to change, which you'll set to 0. Okay. Alright. So it'll be this. And wait, okay, so we're reading the register first and then we're doing it for program counter. Reading all this first. And masking it with the hex of this. That should be right. So, I'm back at there, so let's continue. Okay, so we did gel and gel R. Let's take a look. So now we actually need memory, bro. If we go to these memory instructions. Damn. How do you access memory? So, I don't think I've ever covered this yet in my computer architecture book, so. Okay, wait, so. Memory meaning like the memory address. Let me see some. Like RAM, okay. Yeah, right, so each one has addresses, so. Why would it be on site 80? Isn't that only like 256 values? So like, if it's signed, it'd be like negative 120 something to 120, and then 256 on regular. Right? So why would it be? So yeah, I just did it in a calculator, but okay, so operate on different sizes. Load word reads 4 bytes, load half word reads 2, load byte equals 1. Yeah, because each like a word is 4 bytes and then half word is 2 bytes. Double word is 8 bytes, and then just load byte is just 1 byte. So dude, I actually really don't know, to be honest. I really don't know for this next part. These elements went by the index to the address. Why? I actually don't know why that would be the case, to be honest. Let me do a deeper look into this. So let's just take one instruction, load byte. So loads an 8-bit value from memory. Then sign extends to 32 bits before storing in the destination register. Okay, so we're first taking 8-bit value. That's why we needed the unsigned int 8-bit value. Okay. But then we're extending that value to the full 32-bit length of the bit string that we had. Okay. Then what is the unsigned version? The unsigned version is just, I'm guessing, just the unsigned version. Only unsigned values. Wait, so... Where should this memory live inside core? Source redundancy cores. I guess it would live somewhere else, right? How would you read multiple bytes from a byte addressed array? I have no clue, to be honest. We're hitting some roadblocks here, but that's fine. We'll figure it out. What even is a byte address array? Like, is it just like memory addresses? Okay, wait. So, okay. Memory is an array of individual bytes. Reading a word 4 bytes means regarding 4 consecutive bytes and assembling them into a single 32-bit integer. This is where endianness comes in. Yeah, that's where like the most significant byte and the least significant byte matter, like where it's positioned. risc-v is little ended, meaning the least significant byte is stored at the lowest address. Okay. Gotcha. So that means the lowest address is stored at the least significant byte is stored at the lowest address. Yeah, that makes sense right here, as you can see. So like the bottom bits, the bits at the bottom are stored. Okay, this makes sense. I read about this somewhere, but I wasn't able to internalize back then, like it fully. But now I think I can. And then we add the address. Wait. Don't addresses like move in 4s, I thought, or no? But I guess it's on the bit level, so it's a different type of address or something, I guess. Okay, it's a different type of addressing. Yeah, byte addressing and word addressing. Word addressing is what we're used to, right? No, byte addressing is what we're used to. Wait. Word addressing, okay. Which is 4 bytes ahead, but just the system itself is byte based, okay. Gotcha, okay. Kind of starting to understand it. Still trying to internalize it a bit, but we're getting there. Okay. So I guess we can start with a memory struct, right? I guess we can. Alright. So it says to implement a new struct, right? We should have a separate memory struct that core holds a reference or pointer to. Okay. So a memory struct like this. And index corresponds to reference to byte address. I need to understand how to approach this. So we need to actually understand the size of each one. You wouldn't be able to get it by itself like that. Okay. Wait, did he ever explain why the number was for that many bytes? 64 kilobits. Okay, so that's just like the number for this arbitrary number, okay. A real risc-v system can use 4 gigs Okay, 4 gigs, yeah. Yeah, because isn't the stack around 4 gigs anyways? Like it's like 1 to no, it's 4 megs in that case. It's 4 megs. It's like 1. It can be like from 1 to 8 megs. You can't allocate a 4 gigabyte. This is like crazy. So yeah, we'll just start with the random value. Yeah, so you can just start with 65,536. We need to make this 8-bit because we're addressing learning 8-bit value from memory. We'll just call it memory. For a function of reading reading the byte, we need to read the byte and how would we move on from this? Okay, so for reading the byte, for each size, right? So what exactly are we gonna need? Let's see. Let me see if there's any hints in here anywhere. So then every individual byte has its own unique address. Also, these addresses accessing words, so we're loading from an address, right? But right now we're reading. Right now we're trying to read a byte. So would we need the address? So like so I guess like it's on int and like accessing the address, I'm guessing, as the parameter. We want the address so we can actually read it. and like we'd just be returning this, right? So we'd be returning this value, like something like this, right? I would assume. It's kind of bit of something you already did for media, it's just with bytes instead of instruction fields. I need to understand how this is. So like this address itself already takes all 32 values. This takes what, like 32 minus 8, and then you have to shift it 8 and so on and so forth. Oh yeah. It's like 4 bytes, not 1. Oh yeah, I was looking at the one for read word. So I guess we can just keep this here for now. Call it read word. I can't lie, it is a bit confusing. Like it makes sense, but I haven't internalized it completely yet. Hopefully I'll get it soon. Understand. So in this case, we're taking an address. If we're reading only 1, right? Okay, so it would not just be okay, wait, so in this case, since we're reading 4 bytes, we need 4 different byte addresses. So in this case, would it just be memory and then like indexing into the address itself? Would we do a shift? Would the address be long enough? Let me try and like make the connection here. So I noticed that for the read word function, we need 32 bits. So no, we need 4 bytes. We can do 4 different addresses, each holding 4 bytes. Or not 4 bytes, my bad, 8 bits. What is the shift exactly? If I can actually like understand what the shift actually is, I can get a mental model of it. Okay, wait, so the address at 1 is bits 15 to 8. So left shifting by a certain amount. So already in the right place. Since the least significant byte here is at the least address space, you don't need to actually shift it, but the rest do need to be shifted. So as we move down address spaces, move to higher address spaces, we will be having more significant bytes. That's what least endian means. So byte returning is assigned into 32. So you're just padding a bunch of zeros. So it's bits 7 is 0, and the rest are just padded with zeros automatically. Okay, I got it. In the case of the bits actually leave the other way, that's why we do a left shift instead of a right shift. Yeah. Oh right, okay, so we're assembling the bit. Okay, I was thinking of the other way. So we're assembling the bits from the bottom up. So this starts, so this would be like these bottom bits. And then we, for each address that we increase by 1, we add more bits to the left. But in the case of our byte here, our read byte here, we just have our, our starting bits, and then we pad the rest with the zeros. So it'll just be like a bunch of zeros, and then just this part. Okay, that makes sense now. I'm starting to understand a bit. Definitely do some reading to understand it better. So now let's implement the same logic with half word. So read half word. So we're going to do the same logic that we had before. So we're taking in the address of that. Okay, so a half word, right? So a half word would be 2 bytes. So we need to read 2 different memory address spaces. So this one will automatically be in place already. It will occupy byte bits 0 to 7. And then not semicolon. We need to do an OR operation and have the next one. Alright. We increase the address by 1, but in the case of this, we need it shifted by left shifted by 8, so it doesn't occupy bits 0 to 7. So essentially, you'd be starting here. Let's just like do random. So it'd be starting here, like a random set of bits, and we'd be shifting it this way. So it'd be like this. Horrible drawing, but it's fine. So it'd be like this, and then pad the rest of the bits with 0. The rest of the 32 bits with 0. I think I got that mental model right now. Okay, so we have byte, half word, word, and I think that's all we really need. I don't think we need double word for this since we're just doing that. Double words for 64 bits. It's 15 to 0, not 15 to 8. Since 6 bits total computation, right? 2 bytes. Well, yeah, that's what I meant. That's what I meant. So we're taking that value. Yeah, got it. Now we have the 3 functions. Okay, now we need to actually write them. So, for writing these values, what we need, like, we'd also need the address itself, and we need to, well, okay, this doesn't need to be that. It can be a void function and just have it print the value. Void write byte, so let's think so. Okay. So this one we access memory addresses and put them in the right place. So now I need to actually write. So this one seems a bit more complicated. Storing as bytes into individual memory slots. So it'd be something like yeah, so extracting a drill byte, you'd use a and mask. So if you wanted the first 7 bits, you'd do a 0 mask for all the other bits and do a 1 mask for the remaining bits. So I guess it'd be like a value. And what exactly are we? Turns bytes into individual memory slots. So the memory address would be equal to Wait, so it'd be the value that we got from there. And what is the mask, right masking? So for masking for the first 7 bits, it'd be wait, no. Other way around, my bad. So yeah, let's just rewrite it. Maybe 7F, would it not be? Max, no, 7 bits right matters. Oh, right. We have to be thinking of 8 bits, not 7 anymore, because okay, yeah, 0xf is the actual mask. That's my bad. That's my bad about the yeah. Missing address parameter. The right functions need to know where to write. Like the read functions take an address. The value tells you what to write, the address tells you where. Okay. Got it. Okay, so in the case of oh my bad. In the case of this, in the read ones, we were just reading from an address, so now for this one we need to write from one, so we need the address parameter as well. And we need to be indexing into the array, the memory array, and then accessing in that memory address value and masking it by a certain amount of bits to grab bits. So then the rest of these are equals value okay, so value so first we have to shift it by 8. Shift it by 8 first, and then do a mask on it. And that mask, so 0, 1, 2, 3, 4, 5, 6, 7, 8. These will all be 0. We need to grab these and then the rest padded 0. So we're grabbing these bytes and masking it. We need to find what that mask is in hex. Should be FF00. Think so, right? I'm doing this right. So we are saying this at that. That will be extracting the second byte. Let's just direction. Wait, so let me get what is stored in value. Like I need to know like a layout of it. The number and you want to write to memory address at address 100. So our value would be 100. Or our memory address would be 100 and you want to store that. Which is that. Wait, so if we're getting that value, why wouldn't we need to shift this value as well, right? Wait, so... Oh, okay, I understand. So starting at the lowest byte. Need to keep addressing down. Okay. Okay, that's why we'd be doing a right shift, not a left shift. So it'd be the same case for these ones too. So moving down the address would be shifting by 16. And that case would be so. Would it just be the same mask? It looks to all just be the same mask, so it's all just gonna be 0xFF as the mask. And finally, address 3. Shifting 24 bits, so it'll be in the final positions from bits 31 to 24. Same mask. Oh, that's right. My bad, my bad. We only need 1 byte for that one. So the rest of the functions will do that. So we have word. Taking in 2 bytes. So writing 2 bytes of memory. And then this one. Right, word. We're writing in 4 bytes of memory. This is just gonna be the one. Okay, now we have something here. Alright, finally. That took like a long time to actually understand what was actually going on. That was quite the pivot. Because like understanding this stuff was fine. I just haven't gotten to this stuff yet in my book, so like I haven't understood it, so I have to like learn it on the fly right now. But I will read it in the book and see. And try to actually like internalize it properly. But for now I think I understand like the basic concept of it. Yeah. Let me just go through it again. Alright, so we're setting an array, and this will be about like 64 kilobytes of memory. And now we're reading each memory address and taking a byte at a time. So for reading byte, we'd be taking 1 byte of memory address out of the memory address. For half word, we need 2 bytes, since a half word is 2 bytes. So we'd have to increase the address by 1 and shift by 8 to shift the bits down. And a word is 4 bytes, so we need to actually extract 4 bytes of memory. So incrementing each address by 1 and shifting it by 8-bit intervals, since each byte is 8 bits. And for the case of writing each of these, you're taking in the value that you want to write into the memory address. You're doing a mask on it to only extract those specific bits, and you're shifting the value if you need to shift the bits down. Seems like a good grasp of it. Let's just ask Claude to do a quick summary of what we just did so I can read over it and see if I actually internalize it right. Physical range, flat rates. How many amount of bytes? Yeah, okay. Memory is byte address. Every individual byte has its own address, right? So each slot exactly 8 bits matching the hardware. Why separate read sizes? Yeah, because different instructions operate on different widths, which matches our risc-v instructions here. Loading a byte, which are loading in 8 bits. Half word, which is 2 bytes, 16 bits, and loading word 4 bytes, which is the full 32 bits that we're doing for the 32-bit string that we have. Why left shifts are reading? Placing each byte as correct bit position in the final 32-bit value. The byte at address plus 1 belongs to bits 50 to 8, yeah. So left shifts 8 and so on. So we're basically rebuilding the bits from the bottom up. I understand that, yeah. Why right shifts from writing? Extracting each byte from a 32-bit value to sort individually. The second byte lives at bits 50 to 8, so you shift right to bring it down to 70. For masking it with 0xff. Okay. I understand. The least significant bytes goes to the lowest address, yeah. That's basically for the architecture. We're a little endian architecture, not big endian. So the least significant byte is at the lowest address. And as we move up the addresses, we increase in our bits. In our bytes, not bits. Well, yeah, also bits, but yeah. I was missing. So sign extension for load byte and load half word. That'll happen and execute when you implement the load instructions. Okay, so since we finally have the function down, we should try and write it in. We'll just try a couple of cases and we'll end the stream off for today. Okay, let's go. So load byte first. Let's start with load byte. So in the case of load byte, what is the formula for it? So we have the destination register which we're setting it the value into. We're extracting the memory from the value of register source 1 plus the immediate that we have. Okay. And how's it instructed? So load byte. So it's just the same here, like this. So I think we can implement that. So let's try it out. So first we have to write to the register. And for the values in here, we don't need this part anymore. So first let's look at the actual value. So we need to read the register from the rs1 value. And with that, we are adding it onto the immediate value that we have for load byte. Now, over this, we need to, oh yeah, before we do that, let me see for a second. Right word, right? Not right word, sorry. We need to read the byte, We need to read byte. 1 second before we do that, I forgot this is the header file, so I've been putting everything in the header file like this. We need to move this all over to the main file. Not core. So now it should actually properly read, and then we can just change these to just the forward declarations instead of having all this values here. I totally forgot that we were working in the header file. I totally forgot. That's my bad. So we can just make these all declarations instead, forward declarations, and then access them. So yeah, it should be correct now, all the stuff, so we can access. Then for the read byte, So first we need the memory address, right? So how do I access the memory address for that? I think it'd just be that, right? Right. Okay. I think I'll store this in a variable. I'll swear. It'll make it much better to read it. And we'll store it as a memory variable, I guess. Just call it memory. Wait, how come it doesn't? It's like the functions declare and everything, so how come it's not reading properly? Oh yeah, wait. I might just be doing something stupid here. That's why it's not working. Let's just check all of this. But I don't need all of that. Oh yeah, we did discuss this earlier, didn't we? Because they're in different structs, so we need to reference or have a pointer to it. Not read by. Okay, so we need to have a separate function. Just like have a reference here, we need a reference to the memory. Just like not cost. And then we need to change the header file in here to the same thing. Okay. Why is it like still not working? So in order to access, we need to do that, but it's not recognizing that anymore. Did we not change it properly? Oh. Wait, so let me read that properly. Memory needs to be defined for recording the header file. Quality from top to bottom. Does it though? Does it fix that? Okay, it does. Alright, that makes sense. I totally forget about like little issues like this. I'm not gonna lie. Alright, since now it's out of the way, we can check the logic for this one. Alright, sign extensions. Oh my god, dude. So this is right for load by unsigned. Static cast everything. Or wait, no. It's not a static cast, is it? No, we're sign extending. Sign extension for 32 bits. So that could say the same, but we need to. So it wouldn't be that, right? Oh no, what would it be? For... Oh wait, this, I keep forgetting, this is not the 32, this is not the 4 bytes version, this is the 1 byte version, so this sound extension would be right for the 4 bytes version, but we need it only for the 1 bytes version, which is going to be 0x80. I keep forgetting. So it should be right now. First, we need a listing. And we're going to be taking what is this value in a binary? So all the way down to the 8th bit, right? So if this one is, okay, yeah. So if this one is declared as 1, this one will be declared as 1, the sign bit, yeah, okay. Oops. I can do the same. Same scenario. Load half word. Load half word's gonna be the same thing, but in this case we are loading half word. Are we also reading the register? We are reading the register. Grabbing those values. But in this case, So I guess it's adding just 2 zeros. Okay. 1,000. Okay. If that's the case, memory would be memory or should be that value. And load Halford unsigned. In the case of this one, it's just this, yeah. Okay, last case of the day before we end the stream. Load word, doing load word, which in this case we have the memory, right? So if memory and 0x should be that, right? I want to check this in hex real quick just to make sure. Yeah. Oh wait, no, it'd be even more, even two more, yeah. If that's the case, we have memory is equal to 4. So would it just be 0? Because you're just checking that or 0, so. I think. Oh, yeah, I keep forgetting, bro. Read word. Yeah, okay, that's what I was thinking. Like, it's kind of iffy because like, why really? There's no point of doing this. So that's why I was kind of like confused. Like, do we really need this? But yeah. So. we're just gonna end the stream off for today. We're gonna stream for quite a while, like around almost 2 hours now. And yeah, I think this is a successful stream. We actually learned a lot. I'm gonna try my best to internalize everything that we learned today, and we'll continue off tomorrow. See you.